All right, we got lesson 2.2.4, dimensional analysis. So I got a little bit of story before this one starts. So back in 1999, NASA sends up this satellite called the Mars Climate Orbiter. So it was designed to fly to Mars and then orbit Mars and pick up readings about Mars's climate and stuff. But something happened to it. It didn't get to its spot. So what happened? Did a meteor hit it? Did it blow up? What went on? Well, something very simple happened to it. The engineers who designed the trajectory of it, how they're shooting it over there, they forgot to convert from English to metric units. Basically, they forgot to transfer miles into kilometers. And so it completely missed hitting Mars at all. And it cost $125 million. So a $125 million mistake based off of a very simple conversion of units. And that's what dimensional analysis is. It's important to get your units right, as the NASA engineers sadly found out with their $125 million mistake. All right, so to start this off, we're going to just start off with a little throwback to our big race. So in the big race, Leslie rode at a rate of 2 meters every second. Okay, 2 meters a second. But, we're in the US, we don't use meters. We use feet or miles or something. So how much would 2 meters per second be in feet per second? Well, in order to know that, you're going to want to go to your books into the methods and meaning section. And the methods and meaning section has a lot of our conversions that we need. For instance, we can see 1 inch is 2.54 centimeters. We can see that 1 foot is 12 inches. You should know that already. So we've got a whole bunch of conversions there. And also some prefixes here that can help you, like centa, like centimeters. Centimeters means there's 100 centimeters in 1 meter. So what we want to do when we do conversions is make ratios. So we know that they're starting off at 2 meters every second. So that first ratio is 2 meters. Make sure that you have your units there for every 1 second. All right, and what we want to end in is feet per second. So the numerator needs to change, but the denominator does not need to change. Okay, well, on this one, they have inches to centimeters. So let's switch this meters into centimeters. In order to switch a unit from the numerator, what we need to do is multiply by the number 1. We know that there is 1 meter for every 100 centimeters. So what this does is, we're going to see this a little bit later, is we are reducing the units of meters, because meters over meters would cancel each other out. So now what we have is centimeters per second. But again, we don't want centimeters per second. We want feet per second. So I'm going to do the conversion for that. But I know inches per centimeter. So I'm going to say that there is 1 inch for every 2.54 centimeters. And again, what we're seeing here is the centimeters up here is reducing the centimeters down here. And again, we're just multiplying by 1 because 1 inch equals 2.54 centimeters. So we're just multiplying by 1 each time and changing our units as we go. Now, it's still not in feet per second, it's in inches per second. So my last thing is I'm going to say, okay, I need to multiply this by 1 foot for every 12 inches. And now inches is canceling out there. So what I can do is I can just multiply going straight across. 2 times 100 times 1 is 200. in the denominator, we got 1 times 2.54 times 12. Let me pull out my calculator. 2.54 times 12 is 30.48. So that's 200 for every 30.48 seconds, 200 feet for every 30.48. Now that's not a unit rate, so we need to take 200 and divide by 30.48. So 200 divided by 30.48 comes out to 6.5616. Let's just round it to the nearest tenth. So we'll just call that 6.6. And we know that the units are feet per second. So those are the only two units left. So that's feet per second. And there we go. There's dimensional analysis, changing from one unit type into another unit type by multiplying by 1. All right, now we're going to start working it out together. So I've shown you how it works. Now you're going to go ahead and do it with me. All right, so we've got 3 people. The tricycle races are over. So what's our next big race? Oh yeah, we're going to race snails because that's what people do. So Terry, Madeline, Matt, and Olivia, they're getting ready for a county fair snail race. Which sounds disgusting. They knew their species of snail could travel 8 feet per hour. All right, 8 feet per hour. I'm thinking that's a unit rate. That would be 8 feet over 1 hour. All right, but the snail race lasts only a few minutes, so they want to know how many inches their snail can travel in a minute. So they want to convert from 8 feet per hour to inches per minute. All right, so I want to take a break. I'm going to pause. I want you to write all the ratios, kind of like these up here, that we might need to go from 8 feet per hour into inches per minute. So what are the ratios that we're going to need, to go from feet to inches and hours to minutes? All right, I'm going to pause and I want you to write them down. All right, so the ones that I wrote down were we can use the conversion of 1 foot for every 12 inches, or we could flip it around and use 12 inches for every 1 foot. It still equals 1, so either one works. Well, we could also use 1 hour is 60 minutes, or 60 minutes is 1 hour. All right, so we got this group of students together. They're working on the problem. And let's say that Madeline exclaims, I think I got this. Here's what I'm going to do. I'm going to start by taking 8 feet for every 1 hour. And then she says, I'm going to multiply by 12 inches for every 1 foot. And she finds out that she gets 8 times 12 is 96. 96. Now what's left? Well, the feet are left there. And then we've got inches per 1 hour. And we're halfway there at this point, right? That looks about right. But we're still in inches per hour, and we need it to be in inches per minute. But some of you might be confused on, well, why am I allowed to just cancel out those 2 feet right there? Well, you have to remember that everything here is multiplication. And multiplication uses the commutative property, which means that it doesn't matter the order that you multiply in. So we could rewrite this into 8 over 1 times feet over feet. See, I'm multiplying the 8 and the 1. I'm just switching the order of those two. So the feet came here and the hour came here, because multiplication is commutative. You can do it in any order that you want. And then I've got 12 inches over 1 hour. So you can see with the commutative property, with me just switching these two, we can see here that the feet, a foot over a foot, cancels anything out, right? So feet cancels out feet. And here we see that we're left with 96 inches per hour. All right, we're not quite there. I want you to finish it off now and put it into inches per minute. All right, and give it to me as a unit rate. All right, so I need a unit rate. All right, I'm going to pause. You go ahead and finish this off. All right, so here's what I have. I have 96 inches over hours, because that's where we left off last time. And then I used 1 hour over 60 minutes. And that left me with 96 minutes over 60 minutes, 96 inches over 60 minutes, which reduces to 1.6 inch per minute. And just to show what we were doing last time, we can see that when we use the commutative property and I switch the hours with the minutes here in the denominator, that this is just the number 1. So if that's the number 1, we can kind of just ignore it, because multiplying by 1 gives you the same number. It's the multiplicative identity. All right, next problem. All right, so let's say that a group of students, they're working on this problem, and they are doing the big race, and they notice that Kristen's rate was 2 meters every 5 seconds. So they get together and they're like, okay, 2 meters every 5 seconds. Okay, so 2 meters every 5 seconds. And we want it in inches per second. And here's their work. They're like, okay, inches per second, inches per second. All right, so 100 centimeters per 1 meter. Okay, that looks right. That makes 1. Okay, that ratio works. They're like, okay, next, 2.54 centimeters for every 1 inch. Okay, that makes 1, so that's a ratio that works. This should give me their answer. All right, so they made a mistake though. That is not actually how you do it. Can you see what they did as a mistake? I'm going to pause it and let you try to figure out why this is not the correct conversion for their problem. All right, did you see what they did wrong? First part, perfectly fine. Their meters here, if we used our commutative property and switched the seconds with the meters, we'd see that meters would cancel out meters and we'd have centimeters per second. So this meter would get rid of this meter. Problem over here is centimeters and centimeters are both in the numerator. We can't commute that and cancel them out. So what I'm left with is centimeters squared on top and seconds and inches on the bottom. The centimeters never got canceled. What this should have been written as, this last one, should have been 1 inch over 2.54 centimeters. And then we could have used the commutative property to get rid of these 2 centimeters, and then it would be inches per second. So that was their mistake. All right, we're almost there. All right, so now I'm going to kind of leave it up to you. We've practiced a little bit. That 1999 Mars orbiter, the one that was $125 million and they lost it, well, that one was 338 kilograms. A kilo. Okay, so what I want you to do is go to your book, look through your methods and meanings. Kilograms, if you don't know what a kilogram here is, kilo means there's 1,000 grams in 1 kilo. Okay, so that's what that's talking about. Okay, so I want you to go ahead and convert from kilograms into pounds. Now this is going to be slightly different on this one because we're going to start with 338 kgs, but notice this is not a rate. It's just a measurement. So we're going to just put this over 1. Okay, so there's not going to be any units in the denominator for the very first ratio that we make. All right, so I want you to set up your dimensional analysis, give me some ratios so that you can convert kilograms into grams using the methods and meanings in your book. All right, so kilograms to grams using methods and meanings in your book. So everything that you need is right here to convert it correctly. All right, so I'm going to pause, set it up, and we'll see how you did. All right, so my ratios that I used were 1,000 grams for every 1 kilogram, and this way the kilograms can reduce, and I'm just left with grams here. And then I use 1 pound for every 453.59 grams. Well, that's pretty specific. And then the grams cancel out, and what I'm left with is just pounds in the numerator, and there is no unit for the denominator, which is what we want because it's not a rate, it's just pounds. So multiplying the numerators, I get 338 times 1,000 is 338,000. And then in the denominator, I have 453.59. Now, of course, we don't want to say that's how many pounds it was. That makes a lot of sense. So we're going to give it the unit rate amount. So we're going to do 338,000 divided by 453.59, and it comes out to 745.16. Let's just call that approximately 745 pounds. So that satellite that they sent up was 745 pounds. And it's still floating up there somewhere today, just not around Mars. All right, we are almost done. Okay, there's a leaky faucet. It's dripping 1 fluid ounce of water every 5 minutes. How many gallons will it leak in a year? Okay, so you are starting with 1 fluid ounce every 5 minutes. You want to end with gallons per year. So the end of yours should have gallons in the numerator and years in the denominator. So minutes needs to be converted to years, and fluid ounces needs to be converted to gallons. It's all in your conversion sheet. Work it out, and then I'll show you the answer. I'm going to pause in 5, 4, 3, 2, 1, pause. All right, here's what I got. So I did it in 2 different colors. The first color is me changing minutes to years. So my first thing is minutes cancels with minutes, and I've got hours. Then hours cancels with hours, and I've got days. Then days cancel with days, and I've got years. So right now it's in fluid ounces per year. Okay, and then I decided to work on the fluid ounce part. So fluid ounce, reduced fluid ounce. And then cup, reduced cup. Quart, reduced quart. And I'm left with gallons in the numerator up here. And I'm left with years in the denominator down here. Now if you multiply all the numerators together, you get 525,600 gallons. And if you multiply all the denominators together, you get 640 years. So divide that, and it would be 821.25 gallons per year. All right, we are on to our last one. Now this last one is going to be a little bit different. I am not going to give you your answer for this one. What I want you to do is in your Google Classroom, where you get this video from, I want you to, in the chat in that one, I want you to give your answer. And let's see how many people can get the correct answer on this. All right, so this one is based off of I guess like a poem. It's written by a guy who was clearly insane. He wrote this called the Jabberwocky, which is kind of famous. but there's a poem called the Jabberwocky. This is not in another language. This is just a whole bunch of words that this dude made up that sound like real words, but really aren't. So here's how the poem goes. This is the Jabberwocky by Lewis Carroll, written in 1872, because back in 1872, they just liked to make up words, I guess. So here it is. 'Twas brillig and the slithy toves did gyre and gimble in the wabe. All mimsy were the borogroves, and the moan rafts outgrabe. Beware the Jabberwock, my son, the jaws that bite, the claws that catch. Beware the Jubjub bird, and shun the frumious Bandersnatch. He took his vorpal sword in hand, long time the maxim foe he sought. So rested he by the tum-tum tree, and stood a while in thought. And as in uffish thought he stood, the Jabberwock with eyes aflame came whiffling through the tulgey wood, and burbled as it came. 1-2, 1-2, and through, the vorpal blade went snicker-snack. He left it dead, and with its head he went galumping back. And hast thou slain the Jabberwock? Come to my arms, my beamish boy. O frabjous Callooh Callay, he chortled in his joy. 'Twas brillig and the slithy toves did gyre and gimble in the wabe. All mimsy were the borogroves, and the momoras outgrabe. Yeah, it's kind of ridiculous, isn't it? So we've got a conversion dimension analysis for the Jabberwock. So this is based off that poem. So we want to find out how many Jabberwocks are there if we start with 5 frumious Bandersnatches. Okay, so we're starting with 5 frumious Bandersnatches over 1, and we want to end with Jabberwocks at the end. Over 1. Okay, so what you're going to use is all these conversions in here. 20 tum-tum trees in the tulgey wood. Tulgey wood. There's 1 Bandersnatch. There's 5 slithy toves and 2 borogroves. There's 2 momrace per Jabberwock. There are 2 Jubjub birds and 200 tum-tum trees. There's 200 momrats on each borogrove. And there's 5 Jubjub birds per slithy tobe. All right, so there you go. Start with your 5 frumious Bandersnatches and use all of these conversions to find out how many Jabberwocks are. Again, you're going to use this into the comments section where you got this this video from on Google Classroom, and we'll see how you did. It's more than 1. All right, so there you go. Thank you very much. The end.